we may become interested in is if we have all these different sets, we might want to know where do they overlap, or what would a set look like if we combine them together. And then if we have all of these sets, maybe we just want to know what's not in one of the sets. So that's the idea of union, intersections, and complements. So let's start off with unions. So for notation, if you want to look at the union of two sets, let's say we have the union of set A and B, we use this notation that would just be read as A union B. But what that would be interpreted as is we're looking for this set that's containing elements of A or B or both. So OR is a key word that comes up when we're dealing with union calculations, or we'll get to calculations in this scenario, just looking at the set for the union, you're thinking OR, which in mathematics can kind of be a little different than how we interpret it in English, but you want to think of it as one thing or the other thing, or it could be both. So looking at unions, it's very inclusive. It includes a lot of things. So usually when we look at unions, it ends up being something kind of big. So let's say we have these sets. A is the set with the color orange, yellow, and red. B is the set with orange, brown, purple. And C is the set with pink, brown, red, orange, and purple. So let's say I want you to find the set A union B. So what I'm going to do is create a set, and when you're looking at unions, what you could do is just grab the outputs from one of the sets. So from A, we have orange, yellow, and red. And then what I'm going to do is go to set B, and we have orange, but I already included orange in the set. So again, there's no repeats, so I don't need to write orange again. It's already in there. Brown, that's a new one. And purple. So now I have this set that includes everything from A, everything from B, and also like orange, which is in both. B union C, what that would look like is take everything from B, so orange, brown, purple, and then we're going to go to C and grab basically everything, but we just don't write repeats. So we have pink, brown's already included, red is a new one, orange is already in there, purple's already in there, so that would do it. So that would be the union, or you talk about this as being a set that represents B or C. Alright, our next one is intersection. Now for notation with looking at the intersection of two sets, the notation we use is an upside down U. So this would be A intersection B. And what we're looking at here is what is in both sets. So this is going to come up with scenarios dealing with and, what's in this set and this set, which interpreting and in mathematics is very exclusive. It's very specific things, and it has to have both things happening at the same time. So with that, intersections are usually something kind of small because it's restricted to things that are both. So if I wanted to find the intersection of A and C, what I'm going to do is I basically need to look at both sets at the same time and just see what's the same. So like set A has orange, set C also has orange. So that's great. That can be included. Set A has yellow. Set C does not have yellow. So with that, I'm not going to include yellow in that intersection. Set A has red. Set C also has red. So I can include red. And then I'm done. So what I kind of did there is I chose one of the sets. You can do either one. I typically go with the shorter one. It's a little quicker by a few seconds. But I started with A and just went through and saw was it also in C. And if you do that, you'll get all of the pieces. So let's do that with B and C. So let's see. I'll go to B and C we have orange. C also has orange. So I'm going to include orange. B has brown, and so does C. So brown works. And purple, which is also in C. And actually with this one, we end up with this property that looking at the intersection of these two is just B. So with that, we end up with one of our sets as the intersection of the two. This is where we could start to see empty sets coming up, like I mentioned in the last video, is if you're looking for two groups that overlap and looking at this intersection, but what if there's no overlap? What if you go through and they don't intersect anywhere? If that happens and you're trying to, let's see, I'll use two letters that we haven't used. Let's say I looked for the intersection of group D and E, and whatever those were, they didn't overlap anywhere, then what you would do is, if they don't intersect, then the answer would be that empty set, that nothing's happening. Alright, and then our last one here is the complement, which is just looking at something that's not in the set. So for the notation with a complement, what we use is the letter of the set that we want to take the complement of, and then it's in the location of like an exponent would be, and then it's just the letter C for complement. And it's always C, so like if I wrote B with C up there, that would be the complement of B, basically representing everything that's not in that group B. And you can even have the letter C with the complement C, and that would just mean the complement of group C, and it would be everything that's not in that set C. So, let's try this out. Oh, some other notation that might come up, like if you have the complement of A, you might see this symbol instead, kind of like an apostrophe instead of the C in that location. That's also a complement. From what I looked at with most of our resources, we use that value of C, so I'll stick with that notation, but just in case you come across something else. Alright, so what we want to find here is, so we're looking for an intersection, so I want both of these things to happen. If I just read this quickly, it would be that I want not B and C. Or rather, what might be more helpful is kind of working that, because in English that interprets a little differently. We want the values in C, so we want to take those values from C that are in C, and at the same time not in B. So I want to see this intersection of things that are not in B, but are in C. So what that means, in fact, let me write these out here. B, and I'll just do shorthand, was orange, brown, purple, and C had all those colors of pink, brown, red, orange, purple. Okay. So I want the things in C, so maybe what I'll do is just start by focusing on, here's everything in C. That works great. But then I want it to intersect with things that are not in B. So with that, I'm going to start taking out the things that are in B. So orange, so I don't want that. Color that brown, don't want that. Purple, don't want that. So I end up with this set that is pink, red, and that's all. And that would represent this idea of colors that are in C, but are not included in set B. Let's look at that again, but using A and B. So in this one, we're going to look at that it's in A and not B. So I'm going to do that again of drawing both of our groups. So A had orange, yellow, and red, and then B has orange, brown, and purple. So I want the colors that are in A, so I want orange, yellow, and red there, but then I want at the same time for it to not be in B, So we have orange, so get that out of there. Brown, which doesn't show up, purple doesn't show up. So now if I have this group that is yellow and red, I have those colors that are in that group A, in that set A, and not included in B. So that's one way to think about it. With these, so many different ways to think about it, but I kind of like to line them up and then just start crossing things out. And with this, we start to see that maybe a visual can be nice for seeing where these intersections occur. Where do they overlap? Where do they not overlap? And that's where we go to our next video, which is about Venn diagrams.